Today we're going to talk about Dimensionality PCA. PCA is kind of a big algorithm that is really useful for a lot of things. One, you can actually do, we'll talk about this in a second, but you can do a bunch of things. You can either do essentially machine learning with it, or you can think of it as a pre-processing step for other algorithms and stuff like this. And it relates very closely to dimensionality, which we'll talk about some of the issues with those kind of things. But kind of know is that so far in the curriculum, because I believe this covers, okay, I'm gonna get this wrong. Is it section, are we at section 34? Is that right? Okay, so yeah, so section 34 is kind of like the first time we actually are looking at unsupervised learning. And the main idea for unsupervised learning, Edward, is probably a review for you, but unsupervised learning basically is different from our supervised learning that we've been doing. And supervised learning is basically, we say, it's usually associated with classification or regression, basically things that are like, here are the things that we're looking at, here are our targets, we know what the value of those targets are, here are the features that we have, either classify this or make a model, for example, regression, a linear regression line, or some other generic like polynomial regression line, wouldn't be a line, but polynomial regression function. And be able to figure out, what these values are and predict on those. An unsupervised learning algorithm basically comes to the fact that you don't know what essentially the target is. You have a bunch of features, but you might not know what exactly makes, for example, classification. You don't know what makes things what. So a classic example is recommendation systems. Like, you might not know what's the thing that you should recommend to each person. So this kind of falls under like a clustering algorithm. So I think the curriculum kind of gives an example of like apples and oranges or fruit, is that in a supervised learning algorithm, you essentially give all the features of like these like fruits, right? Apples, oranges, pears, bananas, all these things. You give all the different attributes, like what color is it? What's the shape? What's the size? How much does it weigh? Those kind of things. And then you would say, for example, this is a banana. For example, this is a pear. For example, this is an apple. For example, this is an orange. And you basically would train off those examples. And then from those examples, say, okay, now that you've learned everything, machine learning algorithm, here's some new data points. And say, here is a new fruit. What is this fruit? And so it's really useful is that you can get pretty good at identifying what an apple is or what a banana is. However, one thing it's really good at doing is figuring out something that it's never seen before. So if you give something like a kumquat, it might not know what that kumquat is, and it might say, well, that looks like an orange to me. Or if you give something like a strawberry, it's like, oh, that's an apple because it's red. Or it's like, oh, it might give you some nonsense looking things like, oh, it's a banana because of machine learning reasons. So this is one of the issues with supervised learning is if you don't give enough information, if you don't have enough classification, you might basically, what's it called? You might not catch those parts. It's kind of like the example I have is when you teach a kid like what a cow is versus a cat versus a dog, and you give them pictures like, oh, this is a dog, this is a cat, this is a cow, those kind of things. And then the first time they go out, in the country and they see a goat and they're like, dog. They're like, no, it's cat, no, cow, no. Because they've never seen a goat before. They don't know what a goat is. They just assume it's one of the things that you taught them. So an unsupervised learning algorithm, basically you say, all right, I'm not going to tell you what things are. You're going to figure out what things are like. So this is where the clustering algorithm kind of comes in. It's like, here's a bunch of fruit, here's a bunch of features, you figure out what fruits are alike. So he's like, oh, okay, well, based on the features, all of these fruits are the same. So they might pick a bunch of apples, but they might also say, okay, here's a bunch of red apples versus here a bunch of like yellow or greenish apples. And they might classify those as two different things based on the features you give them. So unsupervised is very powerful in this way, but also it can kind of, can be very intensive in the sense like you also have to understand like what are you exactly looking for. You could try to say, for example, if you are predicting saying, oh, oranges and apples, you might get more than just two classes. You might get red apples, green apples, and so on and everything like that, right? So that's kind of like the difference, the big difference I think for unsupervised learning. And with unsupervised learning, we can do a whole lot of really cool things, but it definitely is a little more, it can be a little more difficult in the sense that you don't know what you're going to look for. And afterwards, even if you get something, you have to kind of figure out, it is not, the algorithm's not going to tell you what those things represent. So a recommendation system, like for example, Netflix is really famous for this. You might have heard before, like Netflix splits different classifications to many, many different points, right? Where there's like, horror with a touch of comedy, you know, stuff like this. And a lot of that might, I mean, obviously they don't tell exactly, but that seems very similar to like an unsupervised learning algorithm where it finds things that are very similar to each other. And you as a person, as a data scientist, have to look at the things that are grouped together. It's like, why are these grouped together? And this is kind of something that you can kind of tease out, basically. And this is where it's it's very powerful, but also can be very, not confusing, but open to interpretation. So that's the hardest part probably for unsupervised learning. But today we're going to talk about basically our first approach is a PCA. And PCA is principal component analysis. And kind of going up front a little bit is that I've heard from multiple data scientists that they think that PCA is one of the most difficult machine learning concepts. I don't know if I agree with that necessarily. And this might be showing more like from like my physics background, is that basically what you're doing with principal component analysis is something called eigenvectors. And we'll talk a little bit about what this is, but first thing I want to talk about is dimensionality and why principal component analysis can be super powerful. So I'm going to start sharing my screen. And do you guys have any questions while I try to find my screen real quick? No? Okay. So cool. And I'm going to make this bigger so it's easier for us to read. Okay. So, all right, so I have this little notebook put together, and this is just a discussion about dimensionality. So it's kind of be a little different from my normal, I think, so sad. So dimensionality, when we really talk about dimensionality, we basically mean like how many dimensions things are. And so kind of approach this problem, and then this will tie directly into PCA. I kind of want to say why dimensionality is a big issue. So if we have a lot of dimensions, it means we have a lot of features. Basically, each feature adds a new dimension to it. And so if we have 100 features, by nature, that data set is 100 dimensional data set. Well, clearly there's a few issues with this, right? One is that's really hard to visualize, right? Is that if we wanted to visualize the data set, you can't visualize 100 dimensions. We can visualize 3 on like a computer and we can understand that. But after even 4 dimensions is not a super easy thing for you to kind of comprehend, let alone like 100 or 50 or whatever, right? So that's one of the issues with with high dimensional data. The second part too, actually is a little more subtle. It's a more mathematical way, but people all have their different ways of explaining this, but basically it comes down to the fact that as you increase in more and more dimensions, data becomes more sparse. And what that sparseness means is that data tends to be further away from each other. A classic example of like why high dimensionality or high dimensions is really kind of unintuitive is something called like sphere packing, or like putting a sphere within like higher dimensional boxes. It's kind of a classic example, but basically I'll give you guys the quick like, you know, strokes of what it is. The idea is that you might have something, for example, going into higher dimensions, you start off with a square and you say, all right, I have one big square, and then I break that square into I'm sorry. Yeah, I have a big old square, like a unit square, break into 4 parts, and I write a circle in each one of those quadrants, right? And then in the middle, I have this other circle. I just realized I have something I can draw. I can probably just draw it for you guys just quickly. So like if I imagine I had a, oops, I don't know why that didn't work. Hold on. Why can't I draw? All right, I'll just draw in the air then if I can't draw. That's good. Oh, there we go. What? Okay, ignore that. I just realized, what screen are you guys? Are you guys seeing a screen right now? I'm sharing.
In the Jupyter notebook.
Is it on the top? Does it say dimensionality, or does it say something else?
PCA copy too.
Ah, that's not it. That makes sense now. Sorry. I can never find my I'm going to share a different one because that's probably why I can't draw on top of it. This is what I wanted you guys to see. It's basically, it's related. We're going to talk about the PCA in a second. So, okay, that should be dimensionality then. All right. So just real quickly, this scenario, because I think it's super interesting, but it kind of gives you the idea of like why high dimensions might be kind of confusing and kind of sparse. But if I have a square like this in 2 dimensions, I split up into 4 parts. And then I basically draw circles that are touching each part. of these inner quadrants, and my drawings are not great, right? But I have these parts right here. They're all touching each other. And I draw a centered circle that's touching each one of those. I can figure out how big that circle is, right? So like you can clearly see it's smaller, right? And then if I expand the 3 dimensions, I can imagine having like a cube kind of like object where instead of splitting into 4 parts, I can split it into 8, quadrants. So you can imagine like I split it here, split it here. So basically I have 8 quadrants, and then each of those quadrants, I have a sphere, and then in the middle, there'll be some space, and like how big of a sphere can I make in that space? And you'll see it's the ratio of that sphere gets a little bit bigger. And I can extend this to 4, 5, 6, 7 dimensions and so on, right? And it turns out as I get bigger and bigger, that inner sphere actually ends up being of higher hypervolume. And basically it's like, it's one of those things like, well, it turns out it'd be more volume than the other outside spheres. And it'll actually poke out of the original cube essentially. And it's kind of a weird thing being like, wait, why is this happening? Because like if you go through the process, you're like, wait, this shouldn't happen. And it basically comes down to the fact that in higher dimensions, we just have more available space for us to access. And so the consequence that when we're talking about data science is that our data becomes more sparse. Our data points tend to be more spread out. Basically there's more area or hypervolume for it to basically expand outward. And the problem with that is that for us to use computers, it can be very computationally expensive trying to find these points and compare these points with each other. And another way you can kind of think about this too is that if we have like a 2-dimensional data with like 1,000 points, we can probably get some information from that. But if we had like 1,000-dimensional data set and we had 1,000 points, that's nearly useless because it's very spread out everywhere going through. So this is kind of the idea is like where dimensionality can be actually a huge problem. So this leads us into PCA. It's like, well, one way we can deal with this is using PCA to lower the dimensionality. But kind of get the idea like what I mean by like dimensionality. Let's consider like this, this random data, right? And so this is randomly expressed, everything like that. And this is more or less kind of just 2-dimensional data, right? I can't summarize this data using just one dimension, right? I have to explain the X and the Y part, right? That seems pretty intuitive, hopefully. So there's no way to summarize this information down. Okay. However, if I look at this data set right here, which is essentially just a line centered at y equals 1, right? If you look at that data, is there any extra information in the y direction? No, right? Yeah, I see you guys shaking your heads. No, there's no extra information here. So essentially I could summarize this data with like essentially just a straight line, right? I can just draw a line through here, and that means that data can be summarized with just a simple line, right? I never have to worry about the y dimension, okay? So kind of going a little bit further than this is, scroll down a little bit. Okay, I have this data set, and I'm sorry, this data set right here. And with that data set, oops, yeah, okay. If I have this data set, you can see here is that there is information, right, in the y direction, and there's information in the x direction, right? But you can probably get what I'm getting at now is that we can summarize this information with a single line, right? And I can like, once I have that line, I could like take that line and like turn it over sideways, right? And that now is a 1-dimensional object, right? It's just a single line. All the information is stored basically on this one dimension. I might have to finagle exactly what this information is, but it might be something like y equals, x plus 1, which is that's how I get the data right there. But basically I can store all the information 1-dimensionally onto this single line, right? So that's kind of the idea is like, okay, even though it's 2-dimensional, right, I can kind of finagle this in the right way to summarize information in 1 dimension. And this leads us to this guy right here. So let me ask you guys kind of an open-ended question. Can I summarize this information into 1 dimension? See you guys thinking. And whatever your thoughts are right now.
I would say no, because it's there's like variation between it, like and you're gonna have a hard time finding a formula to get that. Good.
Okay. And I think that's just about right. Is that you could technically try to find a formula. Like I could try to find like an equation that would do this. And there's a fact that you can create a function for whatever you want. But basically that formula is essentially trying to parameterize the information. If I wanted it simply like in a simple 1 line, right? I can just draw like a line through here, but that will never completely encompass all the information. It's a little bit of random noise and stuff like this, right? So the thing is, though, if it's kind of random noise, if we think of it as noise, we can say like, well, we can kind of squish it down to one dimension, but we'll lose some information, right? Like Edward said, we'll lose some of that little kind of fluctuation and stuff like that. So this is arguably say, well, we could, like, we technically can't summarize all of the data perfectly into one dimension. However, if we're okay losing a little bit of noise, a little bit of information, we could like kind of like estimate saying, well, we can get it basically to one dimension, right? And that's what my estimation is here. But you're absolutely right. You can't summarize this whole thing. So, and then our last one here, and this is a little tricky, is that I might have a data set that looks like this. And I'm just going to say this is that you probably would say, oh, maybe it's one dimensional because I can, like Edward was saying, you could draw like a line. But in a lot of ways too, if I wanted just I could draw like a function, you know, and figure this exact out and then draw this as one dimensional. Classically, we tend not to think, I mean, you could think of this one dimensional, you could think of it possibly two dimensional. If you were to think of it like in a straight line sense, there's some information that we would be missing by trying to do this part. And so in principle, I'm going to say is that this would be probably considered one dimensional if we have the right tools to basically get those extra curves and stuff like this. And one thing I'm going to say is that PCA, which is what we'll use to basically, essentially what I'm going to tell you is like take that dimension and squeeze it down into lower dimensions. PCA can't do this. It couldn't summarize along the curve. It has to be along straight lines. Basically come from the fact that a PCA is developed from a linear transformation. And it's going to be a linear transformation of the covariances, which we'll talk about in a second. But just know that PCA cannot summarize this data. It will lose information along these curves kind of deal. But that's okay for some things. Sometimes like, well, we might lose some information, or we might want to transform this data with a nonlinear transformation before doing PCA, or using other dimensionality reduction tools that are beyond PCA. But just know that this would, like, technically you can get in one dimension, but in PCA we say, well, we're just going to lose some of that information by trying to summarize it along these lines. Okay. So any questions about dimensionality of like how these things can be kind of essentially more or less put into one dimension? Okay. And so you can expand this outward to like 3 dimensions and say, okay, well, we're going to basically squeeze down the information into, you know, smaller dimensions, stuff like this. And this is where PCA in particular, let me go ahead and open, no, that's not it. Here it is. Let's go to 3 PCA. And we're going to open this guy. All right. So this is where this is the principal component analysis. So we kind of said like one of their issues with PCA, or not PCA, dimensionality. High dimensionality basically means that it's going to be harder for us to be able to consider, like, to visualize, to also make predictions off of computation, because this is higher computation. And going further into more algorithms, for example, support vector machines, it's usually better for us to be able to summarize this information. Higher dimensionality just tends to be not as great for the algorithm. It tends to work slower. So PCA, principal component analysis, essentially allows us to squeeze that information down, right? And so again, kind of I drew that same picture before. PCA essentially will draw like these axes, right? And we call them components, right? The principal component analysis. Basically, we'll figure out these axes. And what this more or less does, it will actually project down the information onto these components. So you can imagine this line gets projected onto here, or this point gets projected onto this line right here, and so on. So eventually our data might look something like this on that one dimension, okay? And so this would be on one component. And it turns out like, well, we can actually, in a sense, not just draw one of these components, we can actually draw another component onto there. So for example, if I had a second component, I could actually capture more information. So let's say I draw another component like this, right? And this component will capture more information onto this line, where it's like, okay, well, we'll capture the information right here, right here, right here, project it onto this component, right? This axis, okay? You can, sometimes we'll talk about as Eigenvectors. They're all kind of like the same thing here. Okay, and so this green line, instead of it being nice and spread out, it'll probably be clustered like around here, right? Where there's a whole bunch of points right here. Okay, and so what we'll do with, and this is where the principal part comes in, is that cool? Like we can actually store all information using these two new like axes, right? This red line and this green line over here, and we can actually store all the information that was in the data set on there, which is awesome. However, it doesn't really fix our dimensionality problem, right? We just took a two-dimensional problem and put it into another two-dimensional problem, but we just have new axes, right? And this is where the principal part comes in. And the principal says, all right, let's try to like, you can possibly like use PCA to basically just produce the same axes, like same number of axes and not reduce the dimensionality. But usually what it's end up doing will get rid of some of the components, some of the axes, to say, well, what has the most information? And in this case, if I were to say this red line and this green line, which of those two would you guys say has the most information about the data? It just intuitively. Which one?
The red line?
Red line. Yeah, I'd say the red line too, right? The red line here, like more or less has a bigger information, where the other one tends to like, there is variance along that kind of like, if you measure on that green, like tilt your head, like that up and down part on the green. And it's like, yeah, there's some information there, but most of the information seems to be contained on that red line over there, right? How the data spread out and everything like this. And this is actually what we end up doing. And the way we kind of define this information is we essentially talk about the variance. So essentially our variance allows us to kind of say, oh, this is how much information is here. The more variance, the more information we have, right? So one way some people will envision this is they'll take we'll take the data, right? And this is a little more structured, but usually you have a little more random data, and you'll draw like, I'm just gonna draw a normal line. You draw an ellipse. For the record, it's an ellipse, not an oval. Ovals are three-dimensional, but I guess you could say it's oval for 3 dimensions. But I'll draw like an ellipse like this and basically say, okay, like I'll encompass all the data. If I had like better data, like more random, like from the original dimensionality part, if I had it like this, I might draw an oval around this kind of data. But just know for PCA, we're just gonna use this one for right now. But the idea here is like, okay, we have this oval, and if you, or this oval, this ellipse, and if you know anything from back from like, I don't know, back maybe in like high school, maybe college, is that ellipses are defined by something called the major and minor axis. So you have like a minor axis here and a major axis here, okay? And you look at that, you're like, oh, that's basically what our components were, right? We had those kind of components. And that's essentially what we're doing with principal component analysis. We're essentially more or less, and there's a few ways we can think about this, but this is one of the interpretations. We're basically taking all the data, putting it in an ellipse, and figuring out what, which axis is containing the most information. And by most information, we say which one has the highest variance. And so we can see it here, for example, on the that original red line, the one's kind of going from the bottom left to the top right, that has the most information, the most variance across that part. And so we say that is our, okay? So that's one way we can think about it. Another way is actually, like what we're actually doing is something called Eigenvectors. So I have a couple of videos here that I suggest. They're from 3 Blue 1 Brown, if you guys know that YouTuber. He does a really great job of showing, what's it called? Visualizing mathematics pretty well. He has a whole series of videos of like, it must be at least like 2 hours long, of like linear algebra. And these in particular, linear transformations and eigenvectors would really help you understand what's going on to help principal component analysis. He doesn't talk about PCA, but understanding what eigenvectors are and linear transformations would really help out. So I just wanted to point that out. And so just know that these axes, these components, these are something called eigenvectors. Okay, like I'm trying to give you guys all the terminology the way it's talked about. Okay, so these eigenvectors are basically like a special kind of vector. And eigen, if you know your German, basically means like proper, the characteristic, like the true thing. And I don't know if true is not the best interpretation, but basically it's saying like these are like the proper vectors. And by when they say eigenvector, they really mean the proper axis. Is that this is the true axis, and the way we say it's a true axis or the proper vector is based on a transformation. Basically, these eigenvectors appear when you have a transformation. So I'm going to kind of summarize exactly what's in this video in like a sentence, essentially, or 2 sentences, is if you apply a linear transformation, a squeezing, a pooling, a rotation, okay, those are all linear transformations. If you do that, you will find that there are vectors or axes that if you put a vector along this axis, it doesn't, like if you imagine like if I take data like this and I squish it like this, and I have lines, they'll all get squished this way. You can actually find that for any transformation, you can always find complex vectors that basically don't get shifted. They only grow or shrink. So they'll either like scale up or scale down. And that's true for any transformation. However, just know, like I said, complex, meaning that there's can be imaginary. So sometimes you'll get no real eigenvectors. But it turns out we can usually find eigenvectors, basically these certain vectors that don't get moved over. And that's why we call it the proper or characteristic. That's like kind of like in a sense like the true axis that we should have been using for that transformation the whole time. And so kind of going through, and this is where like the curriculum, I'm not going to go through the whole curriculum of what's going on, but if you read through section 34, I believe they start talking about the covariance matrix. And so Edward, you're the one who's gone through part of it. You recognize that word, right? Covariance matrix.
Yeah.
Yeah.
Quick question.
Yeah.
For eigenvalue, is that like when you like transform the actual matrix to like the identity matrix? Is that what the eigenvalue is?
So I'm going to give you the formal definition just to kind of put it out here. Is the eigenvector basically says there's a transformation, and usually it's written with the letter A. Just know I'm using the same kind of notation that you'll see like in textbooks. If you have some transformation A, which is a matrix, basically all linear transformations can be written as a matrix. So I have this matrix A, and I transform a vector, right? And I already said what this vector is, but I transform some vector, right? This is going to equal to some constant lambda, okay, times a vector. And basically what this is saying, if I transform this particular vector, all it will do is it'll scale it up by some number, some number lambda. And the V itself is that eigenvector. So that's kind of what's going on here. It's basically saying under a certain transformation, what are the vectors that will only be scaled? Because some vectors, like if I were to transform, the vectors will now point in a different direction. They're no longer just scaled. They're kind of pointing in different new directions. But eigenvectors will continue to point in the same direction. They'll just be either extended or shrunken down. So that's kind of like the intuitive idea of eigenvectors. I think what you might kind of be going at is sometimes doing eigenvectors, it'll be written as this. That look familiar then?
Oh, yeah. Now, lambda, it's just the name eigenvalue. I just can't remember that. Is that the lambda?
That's right. This symbol is called lambda. It's a Greek letter. But yeah, it's the eigenvalue.
Okay, yeah.
And basically, the eigenvalue is just saying how much does it get scaled? How much does the eigenvector get scaled by under this transformation A? And for principal component analysis, we look at a very specific transformation. We do a transformation called the covariance matrix. I'll just call it like capital C, right? So basically, we transform the data with the covariance matrix, which we'll talk about in a second, and we say, okay, we transform it and say, what are the vectors that are the eigenvectors? What are the things that don't adjust their direction? They only change their magnitude. Basically, are they expanded or they shrunk down? And we do this under the covariance matrix. And that covariance matrix is kind of like, so I'm just going to write the covariance matrix. This is kind of equal to, and I'm just going to put the COV, that's usually how it's notated, of like the X components, I'll put X0. These are all the different features, X0. And then we would have the covariance, and I might get this wrong just so you know, so double check this. X0, comma X1, okay? And then we'd have another part, the covariance of X1 and X0. And then the final one down here would be covariance of X1, X1. And that is our covariance matrix right here. And basically, the idea here is not so much like, why are we getting this specific matrix out? There's specific reasons why we do this mathematically, which, to be quite honest, just takes more linear algebra. Like, linear algebra is a very dense topic that you can go, take a lot, take a lot of time to explore linear algebra. But the important part here is to understand this covariance matrix encodes information about how much variance is across, basically, for our different, in our data set, basically how much information is contained. And so we transform our data to essentially encode information saying what has the most, what's it called? What has the most information or the most variance in it? And then we say, what are the eigenvectors for that? And what this allows us to do is that we actually find that the eigenvectors will become our components, our principal components. Okay, and I should really say components because we haven't talked about the principal part. But basically, your eigenvector, this allows you to find the eigenvectors for the covariance matrix, which basically is saying those eigenvectors are telling you which things have the most information on it. And then from those eigenvectors, we create our axes, basically our new axes that we're going to use from now on. And the reason why we call it principal is because what we'll do is we'll only take the eigenvectors that scale the most. Basically, the ones that scale the most means that they have the most variance within them. So that's kind of why we call it the principal. Principal just meaning like the most important feature along this line. So that's kind of like the mathematics of what's going on here, which, to be quite honest, is not an easy thing to comprehend. Like, it definitely takes, like, what's it called? Like, I feel like understanding linear algebra is kind of like a dense part of it. And the good news is that at least applying PCA does not require you to do the linear algebra part. It's nice to know how it's done and where these parts are coming from. But the main thing, if I were to summarize the whole deal of like, what is principal component analysis in terms of mathematics, you're essentially trying to find what eigenvectors under the covariance matrix. And the covariance matrix basically encompasses how much information, how much variance is in the data. And you find the eigenvectors that of that covariance matrix transformation. And then say, okay, I'm only going to take the biggest eigenvectors, basically the ones that are scaled the most, which means that they contain the most information because they're the ones who get scaled a lot. And that means that they contain the most information, the most covariance in those different features. So that's the mathematical part, which in my opinion, like, I don't know about you guys, but just hearing that does not sound like it makes like, well, what are we trying to do? Like, what's the whole point? I don't know about you guys, if that makes sense, but hopefully the mathematics in the sense you kind of understand, like, okay, we use the covariance matrix to find how much our data varies, okay? And then we have something called the eigenvectors, which is some mathematical thing that allows us to say, all right, what direction does this variance change the most? And those are our components, basically our principal component, and then our components itself. Okay. Any questions on that general part? Like, I mean, not general, but like the mathematical section. Okay. And I would say, I don't expect you to like also know PCA if you've never seen it from me talking about this. Definitely go through the curriculum where they go through a lot more steps. It definitely takes some time to understand what's going on. I would suggest linear transformations and eigenvectors from these two videos that explain it really well. It's like, what are you trying to find? And then say, okay, but my linear transformation is the covariance matrix. Okay, and just know that the covariance matrix is encoding information about how much information is on these different axes. Okay.
The other side of it is if you do actually understand linear algebra, it totally makes everything make so much sense. So
yeah, yeah, definitely. This is the thing. Like this is why I feel like it kind of holds me back. Is for like I have a physics background, we would only do eigenvectors, eigenvalues constantly, and to me this just seems like, oh yeah, this is how you would figure out this transformation. If you're not coming from a linear algebra background, it's definitely not like super intuitive. Like, wait, but what's going on and why are we doing this? So I want to kind of go back a little bit and say, okay, what does PCA actually mean? Like, what does that mean? Like, if I explain this to a high schooler or even like a middle schooler, like, what are we trying to find? So I'm going to kind of back up a little bit. And so this is where I have this example. Like we had back in module 1, if you guys remember, we had the housing, the King County housing project, right? Where we basically had all these bunch of features, right? And I think I even said, like Assad, you might remember this, is that I said that there's some ways we can reduce the dimensionality, but we haven't talked about this yet. This is the way of PCA. And so if you are trying to sell a house, for example, what are some features, like, you know, what are some like aspects of the house that would help you figure out how much that house costs? So you might say like, oh, how big is the house? And big can be like general, like big could just be literally how many square feet, but it can also be like how big does it feel, right? So for example, if you have a house with a lot of windows can make your house feel bigger, right? Or something along those lines. Or like, you know, it could even be something like saying, oh, how much of a yard you have. Like, well, if your yard's very big, maybe you can perceive the house as bigger, or like this concept of a bigger house, right? Like it sounds like when I say the size, it seems very like, oh, quantitative, but you think about like what size means to people, it's kind of fuzzy. It's not super like, oh, one specific feature is the size itself, if that makes sense. Another aspect, which is kind of close to this, is your neighborhood. Is it like, what's the first thing that people usually ask, like, you know, about a house? Like, oh, is it in a good neighborhood? What does that mean? Good neighborhood could mean a lot of things, right? Could mean good school, could be the safety, could be, you know, what are the people around, you know, like, you know, are the houses also like, you know, similar value? You know, are there good parks around? These are all different neighborhood aspects, right? But there's no one feature that says neighborhood. But you can kind of think that those are probably the big aspects of like how much a house costs. It's like size and like its neighborhood, maybe just some other things like quality that would factor in, but then those would probably be like the big factors, right? So the idea with PCA, or like even though it's not anything about PCA, is that you would like to be able to combine these features. Okay. These features, like for example, oh, it was square foot, number of rooms, right? And factor that essentially into like size, right? So these are all my features. Like I have 4 features here, like square foot, number of rooms, school ranking, and neighborhood safety. And there could be a lot more. But I wanted to kind of like say, well, these things are kind of related, and let's kind of make that into like one feature, okay? And then you can think like school ranking here can go into neighborhood, and then the neighborhood safety into this kind of feature here. So the idea here is that I summarize these guys into 2 main features, these 2 components. Now, in reality, I'll probably lose some information, right? Like for example, if I put like number of rooms in square foot and try to combine them in some way plus some other stuff, there might be some subtlety that I might lose. But since size and neighborhood are pretty big, like the main like features, like the main things that really people care about on the house, it's okay if we lose a little bit of subtlety. And that's again what PCA does. PCA basically allows you to lose a little bit of information, but basically be able to say, oh, I'm only going to consider these 2 things. And using these 2 things, then we might be able to predict the house price a lot about just as well if we try to do every single part, okay? And that's really all PCA is doing, is saying, all right, here's a bunch of features, okay? Let's try to combine these features together into basically one mega feature, okay? And what these mega features will predict. And when we do PCA, we usually don't use all of the components that it creates. So like PCA, by its nature of the algorithm, and you can do this with sklearn, you can get all of the components, basically as many components as there are features. But the problem is like, if you do all those components in there, it's kind of like, well, it's like you're not really getting information, you're basically just like transforming the information. So we drop some of the components and only keep the principal, the highest ones with the highest amount of variance, the highest amount of information. And that will predict, we say like, well, we're keeping most of the information. And what's kind of interesting is by nature, because of the fact that we have, we had high dimensional data sets, is that we're okay losing some information because now we can actually do efficient algorithms and work off of those components themselves. Okay, but this is kind of like if I were to explain to a middle schooler, basically, we're trying to find these things called latent features, like the big features, like say, oh, size and neighborhood of a house. And we use our other features to create these latent features, like, you know, oh, we factor in the square foot, oh, we factor in the number of rooms, you know, oh, school ranking, neighborhood safety, you know, how many parks there are, that would be like the neighborhood. And we factor those in to make these big features, and we don't have to worry about all the little details. Okay, hopefully that kind of makes sense and intuitively, like why we're doing PCA. Okay, and really, like I said, that's what PCA is. Essentially, we're just trying to find features like better, like a combo feature. Now in reality, I said like, size and neighborhood. PCA is like, even if like PCA is trying to encode for size and neighborhood, in reality is that just by pure mathematics, is that you'll probably have some mixture of like size and neighborhood together. You wouldn't say, oh, this component is just neighborhood. It'll probably be like, if that was the main feature, it'd be like a combination of neighborhood and size. And the other component would have some combination of size and neighborhood as well. So just know by doing that, you don't necessarily have like this super feature that it's what intuitive by people. And that's because of unsupervised learning. We're just basically figure out what's the best thing to do. And the best thing to do might not necessarily be exactly what's intuitive for us. Okay, so that kind of leads like why, like how you can think of principal component analysis, kind of reviewing a little bit when you should use it, right? It's basically to get like latent features, right? So that's one way. It's basically get latent features so we have like an overall like super feature and predict on that part. So this can think of it like a pre-process. We also can think of it like dimensionality reduction, right? So one reason why we do a dimensionality reduction is to visualize, like I said, like if we just want to be able to, all right, we have our whole analysis, but we want to like visualize what this looks like. Because again, people are very visual, and it's good to be able to express this and be able to, have this intuitive sense of the data. We can actually visualize higher dimensions with this now, because we can basically sum it down into smaller dimensions. We can also reduce noise. So for example, like I showed you, like with the data set where there's a bunch of little parts, with principal component analysis, we basically will remove one of the components or multiple components to basically get rid of that noise. So we project our information down onto one axis and reduce the noise that would have been in that direction. So we can reduce this part. And then again, pre-processing, right? We can pre-process for better performance. So because we have less features to do, we basically don't have to have the computer work as hard, which can be super useful when we're basically doing a lot of machine learning algorithms where essentially all you're doing is basically the computer is more or less tweaking it dependent on the cost function. So as you want to decrease the cost, the loss as much as possible, and to keep iterating over and over. If each iteration takes 1,000 times longer, then your whole algorithm is going to take a long time for it to find the minimum. And so this kind of helps us with the better performance. And we're usually okay with doing that because more or less there's probably noise that we wouldn't be able to predict off anyway. So we might as well just reduce it down. So it's actually more computationally efficient, more computationally viable to determine those kind of like predictions. Okay. So any questions overall on anyway, this kind of sums up what I want to talk about.
So you can pretty much reduce your dimensionality down and like almost make like heat maps or like some type of surface. Would that be one aspect of like what you're trying to really do?
Can you explain a little more like what you're thinking?
Like, I'm just trying to think of how like visualize some of like the project aspects of not only for like multi-collinearity, but like just like when you're trying to optimize, like what I'm trying to optimize is like credit ratings and like the chances of these people paying back their loans, and like taking all kinds of different features and kind of delivering like just what's the chances of you getting your money back with a little bit of interest. So like, could you like use like PCA to kind of drop down to like just give something much more simplistic like this?
Yeah, I think I hear what you're saying now. Usually when we talk about a heat map, that essentially by nature, if you have a two-dimensional heat map, essentially is 3 dimensions, right?
Right.
That's kind of what's going on. But you can say something along lines like credit fraud, or I can't remember the exact, like if someone's going to default on their loan or something like that, right? You can think of it like you can get these latent features basically from all these different features, all these different information, their age, all these different information, right? To figure out, oh, how likely are they going to default? You might think like, well, there's some features, for example, like how trustworthy they are, right? It's like, well, that would be a latent feature, right? You might also say something, oh, like how much money they have available or something like that, or something like a little more vague, like how like financially capable they are, right? Like financially, how do you say, financially secure.
Income. ratio and that sort of thing, their credit score.
Yeah. So like there's a few things in here, like how financially secure they are, how trustworthy they are, but those things I just kind of said out loud, they're not a direct number or like metric that I can say, oh, like this specific feature will fit this. PCA basically will create things like this. Like it's not literally creating trust or
yeah.
and stuff like that. But yeah, you would definitely could take that information, all these extra features, create latent features, and then be able to say basically based on this component right here, basically combining these different features, we can now do a decent prediction on top of it. Versus like if you had like 1,000 features, it might be nearly impossible for you to actually run an algorithm or run an algorithm.
Start lending more money to poor people. They're better than we think.
Yeah. So like there's all these like things you can kind of go from there. But the important part is basically, for at least for PCA, is that we sacrifice some noise, losing some information, but we start with, we get rid of the smallest component. So like the smallest eigenvalue, and say, well, there might be some little fluctuation that we could explain for, but by getting rid of these, what's it called? Some of that extra noise, we can actually do algorithms. And that's kind of, I think, the general thing for data science in general is you're sacrificing between saying, you know, the data are data, right? The data and essentially are the real world, right? It is the real world. But we can't always do everything with the exact nuances of the data. So we have to summarize it in some way, you know, to be able to make predictions, to basically do extra things. And PCA is one of those really strong tools that we can use.
All right. Thanks so much for your help.
No problem. Okay. Do you guys have any other questions before I kind of stop this? No? All right. So I'll go ahead and stop here.